The remaining demos were all written using a system developed by Marc Brown and Bob Sedgewick at Brown University called BALSA, which is an acronym for the Brown Algorithm Simulator and Animator. BALSA provides a framework for creating interactive simulations of algorithms. The Sutherland-Hodgman polygon clipping algorithm uses a meat cleaver approach to polygon clipping. On the screen now, we see two polygons. The one with dashed edges is called the clip polygon. This polygon defines the clip region. The polygon with solid edges is called the subject polygon. We want to clip the subject polygon against the clip polygon. First, we will see a general overview of the algorithm, and after that, we will look at it in more detail. Conceptually, the algorithm trims away all pieces of the subject polygon that lie outside of the clip region. At each edge of the clip polygon, we take our mathematical meat cleaver and hack off any part of the subject polygon that lies outside of the clip region. The thick black line across the bottom edge of the clip polygon represents the first cutting edge. As you can see, any part of the subject polygon that is below the cutting edge gets wiped out. All parts of the polygon that are above the infinite line on which the clip edge lies are saved and checked against the next clip edge. The polygons remaining after all cuts are made is the final clipped region. In this case, we made 4 cuts corresponding to the 4 edges of the clip polygon. Now we'll look at the algorithm again in more detail. To clip against one edge of the clip polygon, the algorithm looks at all adjacent pairs of vertices on the subject polygon list. Each cutting edge splits the plane into 2 half-planes, one which wholly contains the clip polygon and the other which contains no part of the clip polygon. If a vertex lies in the half that contains the clip polygon, we say that that vertex is inside the cutting edge. If it lies in the empty half-plane, we say it is outside the cutting edge. There are 4 possible conditions which can arise for each pair of vertices. In this diagram, the dotted lines represent the edges of a clip polygon, and the line segment with the numbered endpoints represents one edge of the subject polygon. We are concerned with the positioning of the 2 subject polygon endpoints with respect to the highlighted clip edge. In this first example, therefore, both vertices are inside of the cutting edge with respect to the highlighted edge. For this trivial except case, we output the second vertex. As in all cases, we ignore the first vertex because we assume that it was already considered on a previous pass. In the second case, the first vertex is inside the cutting edge while the second vertex lies outside. We want to output the point where the edge intersects the clip boundary. Here, both vertices are outside the cutting edge and we do not output any vertices. Finally, the first vertex is outside while the second lies inside the cutting edge. In this case, we need to output the point where the edges intersect as well as the second vertex. As the algorithm proceeds to process vertices, it outputs new vertices emitting the ones that get clipped. The new view, on the right, shows the output vertices as they are generated and the new polygon as it is created. As we step through the demo again, we will see what happens in each of the 4 cases previously mentioned. We can pick an arbitrary vertex and label it as the first and the next as the second. The edge defined by the first and second vertices is highlighted and labeled. In this case, the first vertex is inside of the highlighted boundary and the second is outside. Since we don't want the point that is outside of the boundary, we will output the point where the subject edge intersects the boundary. As we move down the vertex list, the next case shows both vertices on the outside of the cutting edge. This is the trivial reject case. We output no new vertices. Moving down the list, the new first vertex is outside and the second vertex is inside. In this case, we need to output 2 new vertices, one because the subject edge crosses the boundary and the other because the second vertex is inside the boundary. The final case, where both vertices are inside the particular cutting boundary, is the trivial except case. We output the new vertex. The remaining vertices for this cutting edge are all trivially accepted because they all lie inside the cutting edge. Once we are done clipping the subject polygon against the first edge, we take the new polygon just created and clip it against the next edge. This is done until the polygon has been clipped against all polygon edges. Using the BALSA speed control, we will clip the remainder of the polygon at a faster rate. Try not to blink. The Sutherland-Hodgman clipping algorithm is a simple algorithm, and, as presented here, it can only handle simple cases. As you can see, our polygon has been clipped to two separate regions connected by an edge on the left. We still need to post-process the final vertex list to remove the extraneous edges. The algorithm can be expanded, however, in order to deal with convex clipping regions and clip regions with holes in them. Another helpful part of BALSA is that it allows a student to step through the code of a program along with the animation. Here we see the same animation as before, but with a new view which highlights the pseudocode as the algorithm progresses.